Right now, gravity is holding you to your chair. It holds the moon in the sky. It keeps entire galaxies from flying apart. It feels like the most dependable thing in all of existence. But shrink down small enough, smaller than an atom, smaller than anything you can picture, and gravity starts to come undone. The rules break. Space itself begins to boil. At this scale, the universe stops making sense. We are going to travel there, into a place where empty space bubbles like water, where a single point crushes physics down to nothing, where time itself may melt away. If this journey blows your mind even once, hit like and subscribe, and ride with us. So take a breath. We are about to shrink past the edge of reality. Let's begin. Hold a small fridge magnet a few inches above a paperclip. Let go, and the clip jumps up and sticks to it. Stop and picture what just happened. The entire planet Earth, 6,000 miles of rock and iron, was pulling that paperclip down, and one tiny magnet, small enough to lose in your pocket, beat the whole world in a fair fight. That little moment hides one of the strangest facts in all of science. Gravity feels powerful to you. It aches in your legs when you climb stairs. It slams you into the ground when you fall off a bike. In your daily life, gravity looks like the boss of every force. Across the universe, gravity is the weakest force there is, by a huge amount. The pull between two tiny particles from gravity is so faint that it barely exists at all. Compared to the other forces of nature, gravity is a whisper in a screaming crowd. Think about how weak that really is. When you pick up a coffee mug, the muscles in your arm are beating the gravity of the whole Earth. Every time you jump, for 1 second, your legs win against a planet. Here is the part that keeps scientists up at night. They do not fully understand why gravity is this weak. The other forces are strong and loud and easy to spot. Gravity is a ghost. It reaches across billions of miles of space, and yet up close, at the size of a single particle, it almost vanishes. For a long time, this looked like a small puzzle, a funny detail, but the deeper physicists dug, the more that weakness turned into a warning sign. It hinted that we might be missing something huge about how gravity truly works, because gravity behaves in a way that feels backward. It rules the big world of stars and planets, and it seems to fade away in the small world of atoms, almost as if there are two different universes stacked on top of each other, and gravity belongs to only one of them. That split is the crack we are going to crawl inside, a crack that runs right through the heart of physics. Everything you are about to see grows out of this one weird truth. The force that shapes galaxies is the same force that fumbles and stumbles when you shrink it down, and no one is fully sure why. To understand the mystery, we cannot stay up here in the world of magnets and mugs. We have to go down, way down, past skin, past cells, past atoms, into a place so small that the words big and small stop meaning anything at all. And the deeper we go, the stranger gravity becomes. Look at your hand. It feels solid, warm, whole. Now zoom in, past the surface of your skin, into the cells, into the long twisting molecules inside them. Keep going. Those molecules are made of atoms, and the atoms are mostly empty space. If the center of an atom were the size of a marble, the nearest bit spinning around it would be blocks away. Your solid hand is almost entirely nothing. Everything you have ever touched is built like this. Your phone, your bed, the water you drink, the air you breathe, all of it comes from the same tiny pieces, stacked and linked in different patterns. Zoom in far enough on anything in the universe, and you find the same small world. So a simple question sneaks up on us. If everything big is made of tiny pieces, then gravity, which rules the big stuff, must come from somewhere down in that tiny world too, right? That is where the trouble starts. When scientists shrink their questions down to the size of atoms, gravity gets slippery. Up here, gravity is smooth and steady. It bends the path of a thrown ball into a clean curve. It swings planets around the sun in neat, endless loops. It is polite. It is predictable. down in the tiny world, nothing is polite. Down there, the rules that run the show are wild and jumpy and full of chance. Particles do not move in clean lines. They flicker, they spread out like fog. They can be in many places at once. This tiny world runs on a rulebook that looks almost insane compared to ours. And gravity does not seem to fit inside that rulebook at all. Picture two families who each speak a different language, and neither one can learn the other. One family runs the big world of stars and planets and falling apples. The other runs the small world of particles and atoms. Both families are real. Both are right, in their own homes. But when you force them into the same room, they cannot understand a single word the other says. For gravity, this is a disaster. Gravity clearly belongs to the big family. It shapes the whole cosmos. Yet everything in the universe is built from the small family, from those jumpy little pieces. So gravity has to live in both houses at once, and it cannot. This is the puzzle that has beaten the smartest minds on Earth for 100 years. Not because they are lazy, not because they are missing one clever trick, because the two rule books of the universe seem to hate each other. To even reach the place where they clash, we have to keep shrinking. We have to go smaller than atoms, smaller than the pieces inside atoms. We have to go all the way down to the tiniest step the universe allows. And it turns out the universe does have a bottom step, a smallest possible size. Below it, distance itself stops working. That size has a name, and what happens there should not be possible. Imagine you have a magic ruler that can measure anything, no matter how tiny. You start cutting. You cut a distance in half, then in half again, and again, smaller and smaller. You might think you could keep doing this forever, splitting space into ever finer slices with no end. You cannot. The universe has a flaw, a smallest possible length. Go smaller than that, and the word length stops meaning anything at all. There is no ruler in the cosmos that can measure below it, because below it, there is nothing left to measure. Scientists call this flaw the Planck length. It is almost impossibly small. Let me try to show you just how small. Take a single atom. Already, an atom is far too tiny to see, even with a normal microscope. Now imagine blowing that one atom up until it is as wide as the entire Earth, 6,000 miles across. A giant floating ball where before there was a speck. At that huge size, the Planck length would still be far too small to ever spot. It would be lost. A dot inside a dot inside a dot. That is how deep down we are going. We have left the world of the small and fallen into the world of the almost nothing. And here is what makes this flaw so strange. It is a wall we can never climb over, no matter how good our tools get. Not because our microscopes are weak, because reality itself refuses to be sliced any thinner. At the Planck length, the very idea of here and there, of this spot versus that spot, begins to fall apart. Think of a photo on your phone. Zoom in close and it looks smooth. Keep zooming, and suddenly you hit the pixels, the tiny colored squares that build the whole picture. You cannot zoom in past a single pixel. There is nothing smaller in the image. The pixel is the end of the road. The Planck length might be the pixel of the universe, the smallest square of reality, the point where you cannot ask what is in between, because there is no in-between left. Now sit with what that does to gravity. Gravity, in the big world, works by bending space. Planets roll along the curves of space like marbles in a bowl. But that trick only makes sense if space is smooth, like a clean sheet stretched tight. If space has a smaller step, a pixel, then down at the bottom, it might stop being smooth at all. It might get rough, grainy, broken into tiny chunks, and a bumpy, chunky, broken space is a nightmare for the smooth rules of gravity. It is like trying to roll a marble across a floor made of jagged rocks. The clean curves shatter. Scientists cannot yet see down to this floor. No machine on Earth comes close. So they build the picture with math, and the math whispers something eerie. It says that at this scale, empty space is doing things no calm, smooth sheet ever should. It says that down here, nothing ever holds still. Because at the smallest scale, the universe is not quiet, and it is not empty. It is a storm. Step back for a moment and look at the whole of science. Over the last 100 years, humans cracked two of the deepest secrets of reality. Two giant sets of rules that explain almost everything we have ever measured. Two rulebooks so powerful that together they built the modern world, from rockets to phones to the screen you are watching right now. The first rulebook handles the big and the fast: stars, planets, light, and gravity itself. It says that space and time are not a fixed stage. They bend, they stretch. A heavy object like the sun presses down on space around it, like a bowling ball on a soft mattress, and the dip it makes is what we feel as gravity. This rulebook has passed every test scientists have ever thrown at it. It is trusted, it is proven, it works. The second rulebook handles the tiny atoms, particles, and the forces that glue them together. It says the small world runs on chance and blur. A particle does not have one clear spot. It has a spread of maybes, a cloud of could be here, could be there. Only when you look does it settle on an answer. This rulebook has also passed every test, down to numbers so exact they are almost unbelievable. It is trusted, it is proven, it works. Two rulebooks, both correct, both champions, and they cannot stand each other. Here is the clash. The big rulebook needs space to be smooth, soft, and bendy, like that stretched mattress. The tiny rulebook says the small world is jumpy, grainy, and full of random flickers. One says calm curves, the other says chaos. One says smooth, the other says storm. For most of the universe, this fight stays hidden. Out among the planets, gravity rules, and the tiny chaos is far too weak to notice. Inside an atom, the tiny chaos rules and gravity is far too weak to notice. The two rulebooks live in separate rooms and never bump into each other. Peace through distance. But there are places where both rules must speak at once. Places where something is both incredibly heavy and incredibly tiny at the same time. In those places, gravity is strong and the tiny world is loud, together in the same spot. And in those places, the two rulebooks scream in each other's faces. Picture a referee at a game where the two teams are playing by totally different rules. One team thinks they are playing chess. The other thinks they are playing football. The referee stands in the middle, blowing the whistle, and gets torn apart because there is no single rule that can judge both games at once. That torn referee is us. That torn referee is all of physics. We have two brilliant rule books and no master rule above them to settle the fight. For now, both keep winning in their own homes, and we live with the crack between them. But that crack is not just a gap in a textbook. It hints that our whole picture of reality is missing a hidden layer underneath, a deeper truth that both rulebooks are shadows of. And when scientists finally tried to force the two together, to make them share one page, the math did something terrifying. It exploded. For years, the smartest physicists alive tried the obvious move. If we have two rulebooks that both work, why not just glue them together? Take the tiny world's rules for chance and blur, and pour gravity in. Mix them, stir. Out should come one clean rulebook for everything. They tried, again and again, and the answer that came back was madness. When they pushed gravity into the tiny world's math, the numbers did not settle into a neat result. They ballooned, they raced upward, they shot toward infinity, a value so large it has no end and no meaning. The equations were basically shouting one word, over and over: infinity, infinity, infinity. In science, infinity in your answer is a scream of failure. It means the math has broken. If you calculate how hard gravity pulls at the smallest scale, and your paper tells you the answer is endless, you have not found a truth. You have found the exact spot where your theory dies. Let me show you why this happens in plain terms. In the tiny world, empty space is never truly still. It flickers with tiny bursts of energy, popping in and out constantly, faster than any clock can catch. For the other forces, scientists learned clever tricks to tame all that flickering, to add it up into sensible answers. Those tricks work beautifully. The math stays under control. For gravity, the tricks fail. Gravity feeds on energy, and the flickers of empty space carry energy. So when you shrink down, the flickers get wilder, and gravity feeds on them, and that makes the flickers pull harder, which feeds gravity even more. It spirals. Each step makes the next step worse. The whole thing runs away like a fire that makes its own wind and roars louder and louder until the numbers burn to infinity. Picture a microphone held too close to its own speaker. You know the sound. A tiny hum gets picked up, blasted out louder, picked up again, blasted out louder still, until the whole room is filled with a shriek that drowns out everything. That runaway howl is what gravity does to the math at the smallest scale. It feeds on itself until it screams. This is the war. This is where a century of genius keeps crashing, not at the edge of the universe, out among distant galaxies. Right here, at the bottom, in the tiniest possible place, where gravity and the tiny world are forced to share one point, and it matters far beyond a chalkboard. That screaming infinity sits at the center of the deepest questions we have. What happened at the very birth of the universe? What lives at the heart of a black hole? Both of those are places where something enormous is crushed into something tiny. Both are places where gravity and the small world collide, and at both, our best math throws up its hands and screams infinity. So physicists are stuck with a haunting thought. The infinity is probably not real. The universe clearly survived its own birth. Black holes clearly exist. Reality does not blow up. So the scream is not coming from the universe. It is coming from a mistake in our own understanding. Something is wrong with how we picture space at the smallest scale. And to find out what, scientists had to look closer at empty space itself. What they found there was anything but empty. Close your eyes and picture the emptiest place you can imagine. Deep space, far from any star. No air, no light, no sound, just cold, black, perfect nothing. That picture is wrong. Down at the smallest scale, empty space is one of the busiest, most violent places in all of reality. It never rests. It never goes quiet. It boils. Here is what scientists have come to believe. If you could shrink down to the Planck length and float in the middle of pure vacuum, the so-called empty space around you would not be calm. It would churn and twist like water at a rolling boil. It would froth like the white foam at the base of a waterfall. Little pockets of space would swell up and collapse, twist into knots, and snap back flat, all in bursts too fast to imagine. Physicists gave this boiling a name. They call it the quantum foam, and that word, foam, is the key to seeing it. Think of the ocean from an airplane window, miles up. From way up there, the sea looks like a smooth blue sheet, flat, calm, peaceful. Now drop down to the surface in a small boat during a storm. Suddenly, that smooth sheet is chaos. Towering waves, crashing spray, foam everywhere. The calm was a lie your distance told you. Space is the same. From our giant size, space looks smooth and empty and still. But that smoothness is only because we are so unbelievably far away from the smallest scale. Drop all the way down to the bottom, and the calm sheet turns into a raging, foaming storm. And this foam is not a wild guess. It grows straight out of the rules of the tiny world, the same rules that build every atom in your body. Those rules simply do not allow perfect stillness. They forbid it. A perfectly calm, perfectly empty space is against the law of the small world. So the vacuum shakes forever because it has no choice. Now bring gravity into this storm, Remember, gravity is bending of space. It works by shaping the smooth sheet, but down here, there is no smooth sheet. There is boiling foam, swelling and collapsing a trillion times faster than you can blink. How is gravity supposed to make clean, gentle curves out of a screaming, frothing mess? It cannot. And that is a huge clue to why the math exploded in the last chapter. Gravity was trying to draw smooth lines on the surface of a storm. Sit with how strange this makes reality. The empty space in the room around you right now, the gap between you and your screen, is not truly empty. Zoom down far enough and every inch of it is boiling, foaming, tearing itself and healing itself endlessly, silently, beneath everything you see. You are floating in a storm so small you will never feel it. The foam raises a chilling question. If space itself is churning and unstable at the bottom, then what is solid in this universe? What is actually holding still? Maybe nothing. Maybe stillness is just a trick played by size. But the storm has a source, a single rule of the tiny world that forces the foam to boil and never stop. And that rule says the closer you dare to look, the more violent everything becomes. There is one rule in the tiny world that sounds almost like a curse. It says that the harder you try to see something clearly, the more you destroy your chance of seeing it at all. Scientists call it the uncertainty principle, and it is not about weak tools or human clumsiness. It is a law baked into reality itself. Here is the idea in plain words. In the tiny world, you can never know everything about a particle at once. If you learn exactly where it is, you lose all knowledge of how fast it is moving. Pin down its speed, and its location smears into a blur. The universe simply forbids you from having both answers at the same time. It hands you one and hides the other. It sounds like a rule about knowing, but it goes deeper than that. It is a rule about being. The particle itself does not have both a clear spot and a clear speed. Reality, at this scale, refuses to fully commit. Now here is the twist that lights the fuse. This rule connects tiny spaces to giant energies. The smaller the patch of space you focus on, the more wildly the energy inside it must jump around. Squeeze your attention into a tinier and tinier spot, and the energy trapped in that spot goes berserk. It has to. The rule demands it. A tiny space cannot hold still energy. The more you shrink your view, the harder the energy inside it thrashes. Picture trying to trap a wild bird in your hands. If you give it a big room, it flies in slow, lazy circles. Squeeze it into a small box, and it panics, slamming against the walls harder and faster. Crush the box smaller still, and the bird beats itself into a frenzy. The tighter the cage, the wilder the creature. Space is like that bird. Focus on a huge region, and its energy is calm and slow. Focus on a tiny region, and the energy goes wild. Focus all the way down to the Planck length, the smallest cage there is, and the energy inside becomes so violent it can rip and reshape space itself. That is the engine behind the boiling foam from before. The foam boils because you are looking so closely that the trapped energy has gone insane. Zoom in, and you force the storm to rage. The looking itself feeds the chaos. And this is a trap with no exit. To study gravity at the smallest scale, scientists must look at the smallest scale. But looking that closely cranks the energy to a scream, which whips space into foam, which shatters the smooth curves gravity needs. The very act of trying to study the problem creates the problem. It is like a lock that jams tighter the harder you turn the key. Feel how upside down this is. In our big world, looking closer means seeing better. A microscope reveals more truth the more you zoom. In the tiny world, looking closer means seeing worse, because your gaze itself stirs the storm. Clarity turns into chaos the deeper you push. This single rule ties together everything we have seen. The weakness of gravity, the boiling foam, the exploding math, they all trace back to this one strange law of the small. And this law does something even stranger than boiling empty space. It lets that empty space fill up with particles that were never there. Particles that come from nothing. Empty space is not empty. You have heard that now. But the reason why is one of the wildest facts humans have ever uncovered. The uncertainty rule from before has a loophole, and reality uses it constantly. Because the tiny world can never fully pin down energy in a tiny space. Energy is allowed to appear out of nowhere, as long as it vanishes again fast enough. The universe lets you borrow energy from nothing, so long as you pay it back before anyone can catch you. And energy can turn into particles. So in truly empty space, particles blink into existence out of pure nothing, live for the tiniest sliver of a moment, and then wink back out, gone. They pop up in pairs, flash for an instant shorter than any clock can measure, and cancel each other away. Then more appear, then more, forever. Scientists call them virtual particles. And empty space is packed with them, a churning crowd of ghosts appearing and disappearing everywhere, all the time, in every inch of the cosmos. Let me make this feel real. In the small gap of space between your eyes and this screen, right now, uncountable particles are flashing into being and dying, over and over, faster than thought. The air is full of them. Solid walls are full of them. The deep vacuum between the stars is full of them. There is no place in the universe empty enough to escape this endless flicker. Picture a dark, still pond at midnight. It looks dead and flat. Then it starts to rain. So lightly you can barely tell. Tiny drops touch the surface, each one making a little ring, a quick splash, then gone. Look closer, and the whole pond is alive with these little appearings and vanishings. Thousands of them, everywhere, endless. That is empty space at the smallest scale, a pond in a constant, silent rain of particles from nowhere. And this is not a fantasy. Scientists have measured the effects of these ghost particles in real experiments. Place two smooth metal plates incredibly close together in a vacuum, and the swarm of particles outside pushes them together with a gentle, measurable force, because fewer ghosts fit in the narrow gap between them. The push is real. It has been measured. The ghosts are doing something we can feel. Now think about what this does to gravity. One more time. Gravity answers to energy. And this whole boiling swarm of appearing particles carries energy, a lot of it. If you add up the energy of every ghost particle in every tiny pocket of empty space, the total is staggering. So gravity should feel all of it. Empty space, packed with all this borrowed energy, should press on the universe with crushing weight. And here sits one of the darkest mysteries in all of science. When scientists calculate how heavy this ghost energy should make empty space, they get a number so enormous it should have crushed the entire universe into a dot long ago, or blown it apart in an instant. The prediction is wrong by more than any prediction in the history of physics. Off by a margin so huge it barely has a name. Yet here we are. The universe was not crushed. It was not blown apart. Something is protecting us from the full weight of the boiling void, and no one knows what. Every force we have met so far has a messenger, a particle that carries it. Every force except one, and that missing messenger is gravity's deepest secret. Every force in nature works by passing something back and forth. This is one of the most beautiful ideas in physics, and once you see it, you cannot unsee it. Forces do not reach across empty space by magic. They send messengers, tiny particles that fly from one object to another, carrying the push or the pull between them. Think of two ice skaters throwing a heavy ball back and forth. Each throw shoves them apart. The ball is the messenger. The force is what the ball creates. Light works this way. The force that lights your room, powers your phone, and holds atoms together is carried by a messenger particle. Scientists have caught these messengers, counted them, and measured them 1 billion times over. They are as real as anything can be. The force that glues the center of every atom together has messengers too. So does the force that causes certain kinds of radioactive glow. 3 of the 4 great forces of nature each have their own messenger particle, found, confirmed, and understood. The messenger idea is one of the greatest triumphs in the history of science. 3 forces down. Their messengers are known. Then there is gravity. Gravity should have a messenger too. If the other three forces send particles to do their work, gravity ought to play by the same game. Somewhere, there should be a particle that carries the pull of gravity from the sun to the earth to you, from one speck of dust to another. Scientists even have a name ready for it. They call it the graviton. There is only one problem. No one has ever found it. Not once. Not a hint. Not a flicker in any machine humans have ever built. The graviton is the missing messenger. The one particle that should tie gravity into the same neat family as the others, and it has never shown its face. It is the empty chair at the table. Three siblings sit there, known and named. The fourth chair is set. The plate is out, but the seat stays empty. Here is why this matters so much. If gravity has a messenger particle like the others, then gravity belongs to the tiny world, the world of chance and blur and flickering ghosts. It would mean gravity is one of the family after all, just harder to catch. That would be a giant step toward joining the two rulebooks at last. But if the graviton does not exist, if gravity has no messenger at all, then gravity is something else entirely. Something that does not play by the small world's rules. Something stranger and more alone than any other force in nature. So the hunt for this one particle is really a hunt for the truth about gravity itself. Find the graviton, and gravity joins the tiny world. Never find it, and gravity might be a lone wolf, a force unlike anything else, hinting that our whole picture is missing a deeper layer. Scientists desperately want to catch one. They have dreamed up detectors and searched the sky and combed through their data for the faintest sign. And what they have learned is enough to make you dizzy, because catching a single graviton, if it exists, might be the hardest task in the entire universe. So hard that it borders on impossible. Say the graviton is real. Say gravity really does have a messenger particle, flying between every object in the cosmos, carrying the pull we feel every second of our lives. If it exists, we should be able to catch one. Build a detector, wait, and snag a single graviton, the way scientists snagged the messengers of the other forces. Then you learn what that would actually take, and your stomach drops. Remember, gravity is the weakest force by a staggering amount, so its messenger, the graviton, would touch matter incredibly weakly too. It would slip through almost everything without leaving a trace. Compared to how easily we catch the messenger of light, catching a graviton would be almost unimaginably harder. A messenger of light gets caught easily. Your eye does it right now, snagging them by the billions every second. That is what seeing is. Catching gravitons would be so much harder that scientists ran the numbers on how big a detector you would need, and the answer is beyond belief. To reliably catch even a trickle of gravitons, some scientists worked out that you might need a detector so massive it would have to be the size of a planet. A machine as big as a world, parked in space, running for years, just to snag a handful of these ghostly messengers. And even that might not be enough. Let that picture form. Not a detector you hold in your hand. Not a detector that fills a room, or a building, or a whole city. A detector the size of an entire planet, thousands of miles across, built just to catch a few of the faintest particles the universe has to offer. We cannot build that. Not now, maybe not ever. So the graviton, if it exists, may be forever out of reach. The one particle that could unlock the deepest secret of gravity might be hidden behind a wall we can never climb. Picture trying to catch a single snowflake falling somewhere on Earth, blindfolded, using nothing but a teacup, and you only get one try. That is roughly how hopeless catching one graviton is. The odds are so thin they barely count as odds at all. And this leaves scientists in a brutal spot. They can write equations about the graviton. They can predict how it would behave, but they may never hold the proof in their hands. Gravity guards its deepest secret behind a level of difficulty that mocks all our machines. Still, the hunt is not fully hopeless. Some scientists think there might be sneaky, indirect ways to spot signs of the graviton without catching one head-on. clever tricks that could reveal its fingerprints even if the particle itself stays hidden. We will come back to those daring ideas later, because a few of them are being tried right now. But step back and feel the weight of where we stand. To settle the biggest question about gravity, we may need a machine the size of a world. The answer might be sitting right there in the fabric of reality, and we simply lack the power to reach it, which pushes a wild new thought to the front. What if we keep failing to fit gravity into the tiny world because gravity is not really a force at all? What if the thing we have chased for centuries is a kind of illusion, a shadow cast by something deeper we have never even looked at? Some of the boldest minds in science think exactly that, and their idea flips everything you know upside down. Here is a thought so strange it took the world's top physicists by surprise. What if gravity is not one of the basic forces of nature at all? What if gravity is a trick, a grand illusion, made by something deeper hiding underneath? For centuries, everyone treated gravity as fundamental, a raw ingredient of the universe, one of the building blocks, as real and basic as anything could be. Gravity pulls. And that was simply the end of the story. It was in the foundation. Then a handful of scientists asked a dangerous question. What if gravity is not in the foundation at all? What if it is more like a pattern that rises up out of many smaller things working together? Something real, something you feel every day, and yet made of parts that have nothing to do with pulling or falling. To see how this could work, think about temperature. Feel the warmth of a sunny day on your skin. Heat feels like a basic thing, simple, real. You can measure it, feel it, live in it. But dig into what heat actually is, and you find it is not a basic ingredient of the universe at all. Heat is just tiny particles jiggling. When atoms move fast, you feel heat. When they move slow, you feel cold. There is no such thing as a heat particle. No basic building block of warmth. Heat is a pattern, a story we tell about countless tiny things wiggling. A single atom has no temperature. Ask how hot one lonely atom is, and the question makes no sense. Temperature only appears when you have a huge crowd of atoms moving together. It rises up out of the crowd. It is real, but it is built from something more basic underneath. Now here is the wild idea. What if gravity is the same? What if gravity has no basic building block, no graviton hiding at the bottom, and instead rises up out of a crowd of deeper, tinier things, the way heat rises up out of jiggling atoms? If that is true, it would explain so much. It would explain why scientists keep failing to find the graviton. You cannot find the basic particle of gravity for the same reason you cannot find the basic particle of heat. There is not one. It was the wrong thing to hunt for all along. It would explain why gravity refuses to fit into the tiny world's rulebook. Of course it does not fit. It was never a tiny world force in the first place. It is a big picture pattern, like warmth, like the shape of a wave, like the roar of a crowd. Ask a single atom to roar, and it cannot. The roar only lives in the multitude. This idea is daring, and it is far from proven. Many scientists are still arguing about it, but it is being taken seriously by some of the sharpest minds alive because it turns our oldest assumption on its head. For all of history, we asked, what tiny thing makes gravity? Maybe the real question is, what deeper thing makes gravity rise up out of it? And if gravity really is a pattern, then it has to be a pattern of something, some deeper stuff, churning underneath space-time that we have never seen. The best guess for what that deeper stuff might be sounds almost impossible. Some scientists think gravity rises out of pure information. What is the most basic thing in the universe? For a long time, the answer was matter, or energy, or space and time. But a growing group of scientists now whisper a stranger answer. Maybe the most basic thing of all is information. Not information like a book or a phone. Something deeper. The raw yes or no, the on or off, the this or that, at the very bottom of reality. Some physicists think the universe, at its deepest level, is built out of these simple bits, like the ones and zeros, that build every image and video you have ever seen on a screen. And from that idea comes one of the boldest claims in modern science. Gravity might rise up out of information itself. We already saw how heat rises out of jiggling atoms. Now push that further. What if the pull of gravity rises out of how information is spread across space? When information gets arranged one way, space pulls. Arrange it another way, and it pushes. Gravity, in this picture, is what you feel when the universe rearranges its deepest bits. Let me try to make this less dizzying with a picture. Think of a huge crowd at a stadium doing the wave. One person stands and sits, then the next, then the next. Watch from high above, and a smooth wave rolls around the whole stadium, like a living thing sweeping through the seats. That wave is real. You can see it, film it, feel the energy of it. But there is no wave particle. No single person is the wave. The wave is just information, an instruction to stand, then sit, passing through the crowd. Take away the people, and the wave is nothing. Some scientists think gravity is like that stadium wave. Real, powerful, sweeping through the cosmos, and yet made of nothing but information passing through a deeper crowd we cannot see. The falling of an apple, the orbit of the moon, the spin of a galaxy, all of it might be the universe doing a kind of wave with its most basic bits. This idea did not come from nowhere. It grew out of one of the strangest discoveries about black holes, which we will reach soon. Scientists found that the amount of information a black hole can hold is tied directly to its size, in a way that hints information and gravity are deeply, secretly linked. That clue set off a hunt that is still going today. If this is right, it rewrites the deepest layer of reality. Space and time and gravity would all be side effects, patterns bubbling up from a churning sea of pure information underneath. The solid world would be the surface of something far more basic, like a movie on a screen, made entirely of pixels you never think about while you watch. This is still a frontier idea. Brilliant people are fighting over whether it is true. No one has nailed it down. But it is one of the hottest trails in the search to understand gravity, and it keeps leading scientists to the same shocking place. Gravity may not be a thing in itself. It may be what information looks like when there is enough of it. Yet information needs something to be written on, some deeper stuff to carry the bits. And when scientists tried to find what that stuff might be, one of the oldest and boldest theories in physics stepped forward with an answer. An answer that says everything you are made of is secretly music. Take the smallest piece of matter you can imagine, a tiny particle deep inside an atom. For a long time, scientists pictured these as little dots, solid specks, the final building blocks, with nothing inside. One of the most famous theories in all of physics says those dots are a lie. It says that if you could zoom in far enough on any particle, you would find it is not a dot at all. It is a tiny, vibrating thread, a loop of energy, wiggling, a string. This is string theory, and it is one of the boldest ideas humans have ever dreamed up. It says every particle in the universe, every speck that builds you and me and the stars, is really a minuscule string, plucked and humming, far too small to ever see. Here is the beautiful part. According to this idea, the different particles in the universe are different notes. A guitar string can play many notes. Pluck it one way, and you get a low hum. Tighten it and pluck harder, and you get a high, bright ring. Same string, different vibrations, different sounds. String theory says the universe works the same way. One kind of string, vibrating in different patterns, becomes different particles. One vibration is a particle of light. Another vibration is a particle of matter. Change the note, change the particle. So in this picture, everything is music. You are a chord. The sun is a symphony. The whole universe is a song played on countless tiny strings, each one humming its own note, and the notes together make up all of reality. It is a staggering, gorgeous idea. Now, here is why string theory matters so much for our journey. Among all the notes those strings can play, one special vibration pops out of the math on its own, a particular pattern of wiggling that behaves exactly like the messenger of gravity, exactly like the graviton we have been hunting. Sit with how huge that is. Scientists did not force the graviton into string theory by hand. They were building the theory for other reasons, and gravity appeared all by itself as one of the natural notes the strings can play. It fell out of the math like a gift. For many physicists, that was the moment string theory went from a strange idea to a serious hope. Here, at last, was a picture where gravity and the tiny world spoke the same language. One theory, one kind of string, and both the small world and gravity came out of it together. If string theory is right, the century-old war between the two rulebooks finally ends. There would be one rulebook after all, one kind of thing, the string playing every note, from the smallest particle to the pull of a galaxy. The dream of joining everything under one idea would come true. But string theory asks for something in return, something almost too strange to accept. For the math to work, for the strings to vibrate correctly and produce our universe, there cannot be just the space we know. The theory demands more dimensions, hidden ones, extra directions, curled up so small we have never noticed them, tucked into every point of space. And those hidden dimensions might explain the oldest mystery we started with. They might explain why gravity is so unbelievably weak, because in this picture, most of gravity is escaping, leaking away, into somewhere we cannot see. Remember, the very first mystery we met. Gravity is absurdly weak. A tiny magnet beats the whole Earth. The force that shapes galaxies almost vanishes when you shrink it down. For 100 years, no one could say why. String theory, with its hidden dimensions, offers a jaw-dropping answer. Gravity feels weak because most of it is escaping into dimensions we cannot see. Let me build this slowly, because it is one of the wildest ideas in science. We live in 3 dimensions of space: left and right, forward and back, up and down. Those are the only directions you have ever moved in your whole life. They feel like all there is. But string theory says there are more directions, hidden ones, curled up so incredibly small that nothing we have ever done could reveal them. They are tucked into every single point of space, everywhere, all the time, wound up tighter than the smallest scale we can reach. Now here is the key idea. What if the other forces, like light and the ones inside atoms, are stuck in our 3 big dimensions, trapped here with us, unable to leave? But gravity is different. Gravity is free to roam into the hidden dimensions too. Gravity leaks out. Picture a drop of ink landing on a flat sheet of paper. The color stays strong because it can only spread across a flat surface. Now drop that same amount of ink into a swimming pool. It spreads out in every direction at once, up, down, sideways, and the color fades to almost nothing because it has so much more room to escape into. Same ink, weaker color. It simply had more places to go. Gravity might be that ink in the pool. In our 3 dimensions, it should be strong, but if it leaks into extra hidden dimensions, spreading out into directions we cannot see, then only a faint trickle of it reaches us. The rest bleeds away into the hidden space. What we feel as gravity would be the weak leftover, the pale color after the ink spread into the deep end. If this is true, it solves the puzzle in one stroke. Gravity is not really weak at all. It is just as mighty as the other forces. We only feel a whisper of it, because most of its strength is escaping into dimensions, hidden inside every point around you. And this is not only a fantasy on paper. If gravity really leaks into hidden dimensions, then at incredibly tiny distances, closer than anything we normally test, gravity might suddenly get much stronger before it has a chance to leak away. Scientists have actually built delicate experiments to measure gravity at tinier and tinier distances, hunting for the moment it surges. So far, they have found no surge, which chips away at some versions of the idea. But the search goes on, pushing to smaller and smaller scales, looking for the fingerprint of the hidden dimensions. Feel what this would mean if it is real. All around you, woven into every point of the empty air, are extra directions you can never walk in, never see, never touch. And gravity, the force pinning you to your seat, is quietly draining into them every second. The weakness you feel is a clue that reality is far bigger than the three directions you know. String theory is one grand attempt to unite gravity with the tiny world. But it is not the only one. A rival idea takes a completely different path, and it dares to say something even stranger about space itself. It says space is not smooth at all. It says space is woven. String theory says everything is made of tiny threads. But there is a rival idea, just as bold, that comes at the mystery from the opposite side. Instead of asking what matter is made of, it asks what space itself is made of. This rival is called loop quantum gravity, and its answer is stunning. Space is not a smooth, empty backdrop. Space is a thing, woven out of tiny loops, stitched together into the fabric of reality. For all of history, people thought of space as an empty stage, a blank container where events happen. The stars, the planets, and you all move around inside space. But space itself is just nothing, and empty everywhere. This new idea shatters that picture completely. Loop quantum gravity says space has parts. It says if you could zoom all the way down to the smallest scale, you would find that space is built from tiny loops of gravity linked together like the rings of chainmail armor, or like the threads in a piece of cloth. Space is not the empty stage. Space is the weave. Let me show you what that means with a picture. Look at a photograph on a screen. From far away, it looks perfectly smooth, a continuous flow of color and light. Now press your face close and zoom in. Suddenly you see the truth. The smooth image is built from tiny separate squares, the pixels. There is no smoothness at the bottom, just countless little blocks, side by side, fooling your eyes into seeing a flow. Loop quantum gravity says space is exactly like that. It looks perfectly smooth to us because we are so unbelievably huge compared to the smallest scale. But zoom all the way down to the Planck length, and the smoothness breaks apart into tiny chunks. Space would have a grain, a weave, a smallest possible piece, just like the picture has its smallest pixel. This flips gravity into something brand new. In this picture, gravity is not a force sitting on top of space. Gravity is the shape of the weave itself. When space bends, that is gravity. And because the weave is made of tiny loops, gravity comes in tiny pieces too, chunks of bent space, woven from the bottom up. The two rulebooks might finally join because space itself would follow the chunky rules of the tiny world. This idea also does something beautiful to the screaming infinities we met earlier. Remember how the math exploded when scientists forced gravity into a smooth space? A lot of that explosion came from being able to zoom in forever into smaller and smaller distances with no end. But if space has a smallest piece, a final pixel, then you cannot zoom in forever. You hit the bottom, and when you cannot go smaller, many of those infinities simply cannot form. The weave puts a floor under the fall. The screaming stops. Loop quantum gravity is still unproven, just like string theory. The two ideas even disagree with each other in deep ways, and their supporters have argued for decades. No one yet knows which, if either, is right, but both point at the same haunting truth from different sides. The smooth space you take for granted may be an illusion, a trick of your size, hiding a grainy weave underneath. And if space really is built from tiny pieces, then something almost unthinkable follows. Reality has a resolution limit. The universe, like a video game or a photograph, might be pixelated at the bottom, which means everything you see could be made of dots. Think about your favorite video game. The world inside it looks huge and smooth. Rolling hills, flowing water, characters that move like living things. But you know the secret. None of it is truly smooth. Every bit of it is built from pixels, tiny squares of color, and the game can never show anything finer than a single pixel. That is its resolution limit, the smallest detail it can ever draw. Now, here is a thought that should send a chill down your spine. Our universe might have a resolution limit too. If loop quantum gravity is right, if space really is woven from tiny loops at the smallest scale, then reality itself is pixelated. There would be a smallest possible piece of space, and nothing finer could ever exist. The universe could not draw a detail smaller than that final pixel, any more than a game can draw between its squares. We already met the size of that pixel, the Planck length, the floor of all distance. In this picture, that floor is not just a limit on our measuring, it is the actual grain of reality, the size of a single dot in the great picture of the cosmos. Let me help you feel how this changes everything. When you wave your hand through the air, it feels like you are moving through a smooth, endless flow of space, with no gaps, no steps, no edges. But if space is pixelated, then your hand is really hopping from pixel to pixel, tiny step by tiny step, far too fast and far too small for you to ever notice. Like a character in a game gliding across a screen, looking smooth, while secretly jumping from square to square underneath. Everything would work this way. Light crossing a room, water flowing in a river, a planet swinging around its star. All of it at the very bottom, moving in tiny steps across the pixels of space. The smoothness of the whole world would be a grand illusion, stitched together from countless little jumps too small to catch. This idea is strange, but it comes with a gift. It might tame the infinities that have haunted gravity for 100 years. Infinities come from being able to shrink distances down forever, with no bottom. But if space has a smallest pixel, there is no forever, there is a bottom. You reach the last dot and can go no further. Many of the impossible, screaming answers simply vanish, because the endless shrinking they depend on can never happen. Scientists are even dreaming up ways to test this. If space is pixelated, then light traveling across billions of miles might pick up the tiniest hint of the grain, a faint stutter from crossing so many pixels. Some experiments watch distant, powerful bursts of light from across the universe, hunting for that stutter. So far, space still looks perfectly smooth, even to our sharpest tools. If it has a grain, that grain is finer than anything we have yet been able to catch. The hunt continues. Step back and feel the weight of this possibility. The solid, smooth, continuous world you have trusted your entire life might be a screen. And you, and everything you love, might be a pattern of dots dancing across it, jumping pixel to pixel, never once feeling the steps. Now we are ready to visit the most extreme place in the universe, a place where gravity grows so monstrous that it crushes everything, even space and time, down toward a single point. We are about to fall into a black hole. Everything we have explored so far has been small and quiet, the whisper of a weak force, the gentle boil of empty space. Now we turn to the loudest, most violent thing gravity ever does. Now we fall into a black hole. A black hole is what happens when gravity wins completely. When a giant star runs out of fuel and dies, its core can collapse under its own weight. Nothing can hold it up. The star crushes inward, harder and harder, until it packs an unbelievable amount of stuff into a tiny space. Gravity there becomes so strong that nothing can escape it. Not a rocket, not a beam of light, nothing. Once you cross the edge, you are gone forever. That edge has a name. Scientists call it the event horizon. It is the point of no return. Cross it, and every path you could ever take, no matter which way you turn, leads deeper in. Escape becomes as impossible as walking into yesterday. But the truly mind-bending part is not the edge. It is what waits at the center. At the heart of a black hole, gravity keeps crushing, and crushing, and crushing. It does not stop when the matter gets small. It does not stop when the matter gets tiny. As far as our best theory can tell, it never stops at all. Everything that falls in gets squeezed down toward a single point of no size, with all its mass packed into a spot smaller than an atom, smaller than the Planck length, smaller than anything. Scientists call that point the singularity, and it might be the strangest place in all of reality. Try to picture it, even though it fights your mind. Take a dead star heavier than our sun, more than 1,000,000 miles across, and crush the entire thing down toward a single point with no size at all. All that mass, all that matter, squeezed into nothing. The density there would climb toward infinity. The pull of gravity would climb toward infinity. Space and time themselves would bend so sharply they seemed to tear. Here is the picture that helps. Imagine space as a soft, stretched sheet with heavy objects making dips in it. A planet makes a small dip. A star makes a bigger one. A black hole makes a hole so deep and so steep that the sheet stretches down into an endless funnel, plunging toward a bottom that never arrives. Anything rolling near the edge spirals down and is lost. And this is where two of our biggest ideas come crashing together at last. A black hole's center is both incredibly heavy and incredibly tiny at the same time. It is a place where gravity is monstrous, and the smallest scale is right there, together in one spot. It is exactly the collision we have been circling this whole time. The big rulebook and the tiny rulebook forced into the same point with nowhere to run. So what happens there? What are the real rules at the center of a black hole? Our best theory of gravity gives an answer, and the answer is a scream. Because at the singularity, the smooth, trusted rulebook of gravity does not just struggle, it completely dies. We left off at the singularity, the point at the center of a black hole where everything gets crushed toward nothing. Now let us look at what our best theory of gravity actually says happens there. It says the numbers go to infinity, the density becomes infinite, the bending of space becomes infinite, the pull of gravity becomes infinite. And in science, remember, infinity in your answer is a scream of failure. It means the theory has hit a wall it cannot climb. The great rule book of gravity, the one that has passed every test for 100 years, the one that guides spacecraft and predicts eclipses and describes the bending of light around stars, works perfectly almost everywhere in the universe. But at the center of a black hole, it breaks down completely. It hands you infinities and then goes silent. The trusted theory of gravity dies at the singularity. This is not a small crack. This is the theory telling you, in its own language, that it does not know what happens here. It is a road that runs right up to the edge of a cliff and simply ends, with fog beyond and no map at all. Let me be clear about why this happens, because it ties our whole journey together. At the singularity, matter is crushed down toward the smallest scale, the Planck length, and beyond. And we learned what rules over the smallest scale, the tiny world, the world of blur and chance and boiling foam. So at the center of a black hole, gravity is at its most monstrous, and the tiny world is right there too, both screaming at once, in the same impossible point. The two rulebooks collide head-on, with nowhere to hide, and neither one can handle it alone. The smooth theory of gravity was built for a smooth universe. It never expected to be crushed down into the grainy, foaming, flickering world of the smallest scale. So when it gets there, at the heart of a black hole, it falls apart. It was the wrong tool for the deepest place in the cosmos. Picture a beautiful, detailed map of a country. It shows every road, every river, every town. It is accurate and trusted across the whole land. But right at the center of the map, there is a spot marked only with the words, "Here, the map ends. Beyond this, we do not know." The singularity is that spot on the map of physics, our finest chart of reality, and it goes blank at the most extreme place of all. This is why cracking gravity at the smallest scale matters so much. It is the only way to ever draw the missing piece of the map. To know what truly happens at the center of a black hole, we need a rulebook that works when gravity and the tiny world collide. We need the thing scientists have chased this entire journey. a theory of quantum gravity, and we do not have it yet. So the center of a black hole stays hidden, sealed behind both the event horizon and the death of our theory, a double lock on the universe's darkest secret. And it gets worse, because black holes do not only crush matter, they seem to do something to information, to the deepest bits of reality that should be flatly, completely impossible. They seem to make information vanish, and that breaks one of the most sacred rules in all of physics. There is a rule in physics so deep that scientists trust it almost more than any other. It says information can never be truly destroyed. This sounds strange, so let me explain what it means. Burn a book, and it looks like the information is gone, but scientists say it is not, really. In principle, if you tracked every particle of smoke, every wisp of ash, every ray of heat and light, you could work backward and rebuild exactly what was on those pages. The information got scrambled and scattered, yes, but it was never erased. The universe keeps a perfect record. Nothing is ever fully lost. This rule holds everywhere. Smash a glass, and the information about the glass lives on in the pieces and the sound and the tiny motions of the air. Reality never forgets. The past is always written into the present, if only you could read it. Scientists rely on this so completely that they treat it as one of the bedrock laws of the cosmos. Then along came black holes, and everything caught fire. Throw a book into a black hole, and it falls past the event horizon, gone forever. The information about that book is now trapped inside, sealed behind the point of no return. Strange, but maybe still okay. The information is hidden, but perhaps not destroyed. It is just locked away where we cannot reach it. But black holes have one more trick, and it turns this puzzle into a crisis. As we are about to see in detail, black holes are not truly forever. Over unimaginable stretches of time, they slowly leak away and eventually vanish completely. They evaporate until nothing is left. So follow the logic and feel the floor drop out. You throw a book into a black hole. The book's information is trapped inside. Then, over ages, the black hole leaks away and disappears entirely. The book is gone, the black hole is gone. So where did the information go? If it truly vanished with the black hole, then one of the most sacred rules in all of physics has been broken. Information was destroyed. The universe forgot. And if reality can forget, even once, then the whole idea that the past is written into the present falls apart. Cause and effect start to crumble. Science itself begins to wobble. This is the black hole information problem, and it has tormented the greatest minds in physics for decades. It pits two rock-solid ideas against each other. On one side, the rule that information is never destroyed. On the other side, the fact that black holes seem to swallow information and then vanish. Both cannot be fully true. Something has to give. Picture a safe so perfect that anything locked inside is sealed away forever. Now imagine the safe itself slowly fading out of existence, taking whatever was inside down to nothing, leaving no trace at all. That is the nightmare. A perfect vanishing that should be against the deepest law of reality. For a long time, this looked like a hopeless paradox. But it turned out to be one of the most important clues we have, because to solve it, scientists have to understand exactly how gravity and information behave when a black hole crushes them together. At the smallest scale, the information problem is a doorway straight into quantum gravity. To see the full danger, we need to understand how a black hole leaks away in the first place, how something that swallows light itself can slowly, faintly glow. A black hole swallows everything. Light cannot escape it. That is the whole idea. So a black hole should be perfectly, completely black, and it should last forever, growing but never shrinking. For a long time, scientists believed exactly that. Then one of the most famous discoveries in physics turned it upside down. Black holes are not perfectly black. They glow, ever so faintly. And that faint glow means they are slowly dying. Here is the beautiful, mind-bending reason why. and it brings back the boiling foam we met near the start of our journey. Remember that empty space is never truly empty. Everywhere, all the time, pairs of ghostly particles flash into being out of nothing, then vanish again a heartbeat later. This happens right at the edge of a black hole too, along the event horizon, that point of no return. Now picture a pair of these ghost particles popping up right at the edge. Normally, they would find each other again and cancel out, gone in an instant, as if they never existed. But at the edge of a black hole, something can go wrong. One of the pair slips across the event horizon and falls in, lost forever, and its partner, left behind on the outside, cannot cancel out anymore. So it escapes, flying away from the black hole as a real particle, a speck of light, born at the very edge. To anyone watching from far away, the black hole appears to be glowing. It is giving off a faint stream of particles, a whisper of light leaking from its edge. Scientists call this glow the radiation of the black hole. And here is the crucial part. Every particle that escapes carries away a tiny bit of the black hole's energy, which means the black hole shrinks, just a little, then a little more. It is leaking itself away, one ghost particle at a time. Let me help you feel how slow this is. For a black hole made from a dead star, this leaking is almost unimaginably gentle. So slow that such a black hole would take far, far longer than the current age of the universe to fade away. Not millions of years longer, not billions. Numbers so vast they crush the imagination, with more zeros than you could write in a lifetime. The black hole sips itself away so slowly that it looks frozen and eternal to us. But it is dying, just incredibly slowly. Picture a single drop of water leaving a full lake once every 1,000 years. The lake looks perfectly still, unchanging, forever. But drop by drop, over spans of time beyond counting, it will one day run dry. A black hole leaks like that lake, only far, far slower. And there is a twist. As a black hole shrinks, it glows brighter and leaks faster. The smaller it gets, the quicker it fades. So at the very end of its long life, after ages beyond imagining, a black hole would blaze up and vanish in a final flash, the darkest object in the universe, ending in a burst of light. This slow death is what turned the information problem into a true crisis, because now we know the black hole really does disappear. The safe really does fade away. So the question screams louder than ever. What happens to everything that fell in? And when scientists looked closely at the escaping glow, they found a new nightmare hiding at the edge. A possibility so violent it might set you on fire the moment you tried to cross. We have been picturing the edge of a black hole as a quiet, invisible line. Cross it, and you might not even notice. According to our trusted theory of gravity, you would sail across the event horizon smoothly, feeling nothing special, and only later realize there was no way back. Then scientists found something deeply disturbing hiding in the math. When they tried to solve the information problem, to save that sacred rule about information never being destroyed, they were forced into a horrifying possibility. The edge of a black hole might not be quiet at all. It might be a wall of fire. This is called the firewall problem, and it grew straight out of the puzzle from the last chapters. Here is the trap scientists fell into. To keep information from being destroyed when a black hole leaks away, the escaping particles have to carry that information out with them. But for the math of information to work correctly, the ghostly particle pairs at the edge might have to be violently ripped apart instead of gently separated. And ripping them apart releases a staggering amount of energy, right at the event horizon. Enough energy to form a blazing wall of radiation around the black hole. A firewall? If the firewall is real, then falling into a black hole would be nothing like a gentle slide into darkness. The instant you touch the edge, you would slam into a wall of energy hotter than anything imaginable and be burned away in less than an instant. The event horizon would be the most violent place in the universe, a sphere of fire wrapped around the darkness. Now, feel the trap this puts scientists in. because it is brutal. Our trusted theory of gravity is absolutely clear. The edge of a big black hole should be a calm, ordinary place. Nothing special happens there. You cross smoothly. This idea is one of the pillars of how gravity works, and scientists trust it deeply. But the rules of the tiny world, the ones about information and ghost particles, seem to demand a firewall, a raging wall of fire at that very same edge. So, we have two of our most trusted ideas pointing at the exact same spot, the event horizon, and screaming opposite answers. One says calm, the other says fire. One says you drift across untouched. The other says you are incinerated on contact. They cannot both be right, and scientists cannot yet tell which one is wrong. Picture walking toward a doorway. One trusted guide swears the doorway is empty air, safe to step through. Another equally trusted guide swears the doorway is a sheet of flame that will destroy you. Both have never been wrong before, and you have no way to test it without stepping through. That doorway is the edge of a black hole, and physics is standing there, frozen, unable to say what waits. This clash is not just about black holes. It is another place where the big rulebook and the tiny rulebook collide and cannot agree. Another crack revealing that our picture of reality is broken somewhere deep. The firewall might be real. It might be a sign that one of our trusted ideas is secretly flawed. Either way, it points at the same missing answer. We do not yet understand gravity where it meets the tiny world. To even attempt to fix, scientists reach for an idea so strange it makes everything before it seem tame. An idea that says our whole universe might be flat. A picture, a projection. They think reality might be a hologram. Get ready, because this is one of the strangest ideas serious scientists have ever taken seriously. Our entire universe, everything you see, everything you are, might be like a hologram, a flat picture, painted on a distant surface, projected into what looks like solid, three-dimensional space. You have seen a hologram before, maybe on a credit card or a sticker. It is a flat, thin surface, but when the light hits it right, a three-dimensional image seems to leap out. Depth, roundness, solidity, all of it appearing out of something perfectly flat. The 3D image is real to your eyes, and yet all the information making it lives on a flat sheet. Some of the boldest physicists alive think reality might work the same way. They think all the information about our three-dimensional universe might actually be stored on a distant, flat, two-dimensional surface, far away at the edge of everything. And the rich, deep, solid world we live in, with all its space and depth, might be a kind of projection of that flat information, a hologram blown up to the size of the cosmos. This astonishing idea did not come from nowhere. It came straight from black holes, from the very puzzles we have been wrestling with. Remember the information problem? Scientists were desperate to understand how much information a black hole can hold and where it goes, and they found something shocking. The amount of information a black hole can store does not depend on how much space is inside it. It depends only on the size of its surface, its outer edge. All the information about everything that ever fell in, written on the two-dimensional skin of the black hole, not stuffed into its three-dimensional insides. That was the clue that lit the fuse. If a black hole stores all its information on its flat surface, then maybe everything does. Maybe the deepest truth of any region of space is written on its boundary, and the inside, the depth, the solidity, is a projection of that flat truth. Maybe the whole universe is the inside of a cosmic hologram, projected from information on a faraway edge. Let me help you hold this. Think of a movie playing on a screen. On the screen, characters run through deep forests, fly over vast cities, fall down endless canyons. The world in the movie has depth and space and distance, but all of it is really just flat pixels on a flat screen. The depth is an illusion built from a flat surface. The hologram idea says our universe might be the movie, and somewhere out there is the flat screen it plays on. Here is why scientists take this seriously instead of laughing it off. When they use this holographic idea in their math, something magical happens. Problems about gravity in our three-dimensional world, problems that were impossibly hard, turn into much easier problems about the tiny world on the flat surface, with no gravity at all. The two rulebooks, at war for a century, suddenly cooperate. One side has gravity, the other does not, and yet they describe the very same thing. It is the closest scientists have come to seeing the two rulebooks as one. This does not prove we live in a hologram. It is still a frontier, still argued over. But the fact that it works so well is a giant clue that gravity and information and space are tangled together far more deeply than anyone guessed. And if space and gravity can be built out of flat information, then maybe they can also be unbuilt. Maybe there was a moment when they did not exist at all. To find it, we have to run the whole universe backward, all the way to the beginning of time. We have crushed gravity inside black holes. Now let us do something even bolder. Let us rewind the entire universe, all the way back to its first moment, and watch what happens to gravity at the beginning of time. The universe is expanding. Every galaxy is drifting away from every other, like dots on a balloon that is being blown up. Scientists have watched this for a long time, and it is one of the most solid facts we have. The universe is getting bigger every second, so run the movie backward. If everything is spreading apart now, then long ago everything was closer together. Rewind further, and it was closer still. Keep going, back and back, through billions of years, and all the galaxies, all the stars, all the matter in the cosmos, come rushing together into a smaller and smaller space. Everything that exists, squeezed tighter and tighter as you approach the very beginning. This is the Big Bang, the birth of the universe. And as you rewind toward that first instant, you reach a place that should feel familiar by now. Everything in the entire universe crushed into a space smaller than anything imaginable. Unbelievable amounts of matter and energy, packed into a point tinier than an atom. Stop and see what that means. At the very first moment, the universe was both incredibly heavy and incredibly tiny at the same time. Every galaxy that would ever exist squeezed down toward a single point, and you know exactly what that combination brings. Monstrous gravity and the smallest scale, together, in one spot, the two rulebooks, colliding, with nowhere to hide. The birth of the universe was the ultimate collision between gravity and the tiny world. It was the singularity of a black hole, but for everything that exists, all at once. Picture the whole cosmos, every star and galaxy and cloud of gas, all the matter across billions of miles, shrinking down, 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 until it fits inside a space smaller than a grain of sand, smaller than a speck of dust, smaller than the smallest scale we have ever discussed. The density beyond counting, the gravity beyond imagining, all of reality balanced on a point. And here, at the first instant, our trusted theory of gravity does the same thing it did at the center of a black hole. It breaks. It hands us infinities. It screams and goes silent. The smooth rulebook of gravity simply cannot describe the birth of the universe, because at that moment, gravity and the tiny world were locked in their fiercest collision ever. This is why understanding gravity at the smallest scale is not just about tiny things. It is about the biggest thing of all, the origin of everything. To ever truly know how the universe began, we need a rulebook that works when gravity and the tiny world crash together, the very thing we still do not have. So the first moment of the universe stays hidden behind a wall of broken math. Just like the center of a black hole, our finest theories run right up to the birth of time and then stop, unable to take the final step. And it gets stranger still, because when scientists push toward that first instant, they find that it is not only gravity that breaks down. Everything breaks down. Space, time, and every rule we know seem to lose their meaning all at once. At the very beginning, physics itself simply stops. We rewound the universe to its first instant and watched gravity break. Now let us look closer at that first instant, because what happens there is even more unsettling than a broken theory. At the very beginning, Everything we know about physics seems to stop working at once. There is a specific moment, unimaginably close to the very start, that scientists treat as a hard wall. Before this moment, our knowledge simply ends. It is the earliest instant we can even talk about, and it sits right at the edge of the smallest scale we have explored this whole journey. Past that wall, going back toward time zero, all our rules fall silent together. Think about what this means. It is not only gravity that fails at the birth of the universe. Every tool we have fails. The rules of the tiny world, which works so beautifully everywhere else, cannot cope. The rules of gravity, which guide galaxies, cannot cope. Space and time themselves, the stage everything plays out on, seem to lose their meaning. At the first instant, we do not have a broken theory. We have no theory at all. Let me try to show why the tiniest sliver of the beginning is such a fortress. At that first moment, the entire universe was crushed down to the smallest scale, the same scale where space boils into foam, where distance falls apart, where gravity and the tiny world scream at each other. So the beginning of the universe was not a calm, tidy starting point, like a runner waiting at a starting line. It was the most extreme place and moment that has ever existed. Everything that is, packed into the smallest, wildest scale there is. Naturally, all our rules shatter there. Picture climbing a mountain into thicker and thicker fog. As you go higher, you can see less and less. Then you reach a point where the fog is so total that you cannot see your own hands. You know the peak is somewhere ahead, but you cannot see it, cannot map it, cannot even tell how far it is. That wall of fog near the summit is the first instant of the universe. We can climb almost all the way to the beginning, but the final step vanishes into total whiteness. This wall is one of the biggest reasons scientists want a theory of quantum gravity so badly. It is the only thing that could ever part the fog. A rulebook that works when gravity meets the tiny world would let us take that final step back past the wall, toward the true first moment. Without it, the birth of everything stays hidden behind a curtain we cannot lift. And this touches something bigger than curiosity. Every atom in your body traces back through that fog. The material you are made of, the material of the stars, of the earth, of everything you have ever loved, all came pouring out of that first instant. So the deepest question of where we came from runs straight into the wall where physics stops. To know our own origin, we have to crack the mystery of gravity at the smallest scale. For now, the beginning keeps its secret. The fog holds. Our best minds stand at the edge of knowledge and stare into a whiteness they cannot yet pierce. But the mystery goes even deeper than a hidden beginning, because if space itself dissolves at the smallest scale, breaking into foam and losing all meaning, then something we never question might dissolve along with it. Time itself may not survive the smallest scale. Time feels like the most solid thing there is. It flows, always forward, never stopping, carrying you from one moment to the next, past behind you, future ahead. Tick after tick after tick, steady and sure. Nothing feels more real than the march of time. But here is a thought that should shake you. If space itself dissolves at the smallest scale, breaking into boiling foam and losing all meaning, then time might dissolve right along with it. To see why, we have to remember something scientists learned 100 years ago. Space and time are not two separate things. They are woven together into a single fabric, one thing, called space-time. They stretch together, they bend together. When gravity warps space, it warps time too. Near a heavy object, time actually runs a little slower. This has been measured with real clocks. Space and time are partners, joined at the deepest level, two threads of the same cloth. So follow the logic and feel the ground shift. We spent this whole journey learning that space falls apart at the smallest scale. It boils into foam. It loses its smoothness. Distance stops meaning anything below the Planck length. But if space and time are woven together into one fabric, then whatever happens to space must happen to time as well. If space dissolves at the bottom, time should dissolve too. That means at the smallest scale, there might be no steady tick, no clear before and after, no smooth flow from past to future. Time itself might break into a foam of moments, jumbled and blurred, with no clean order at all. Let me try to picture this, even though it fights everything you feel. Imagine a river flowing smoothly downstream. That is time as you know it, carrying you forward, always in one direction. Now zoom in on the water at the tiniest scale. The smooth flow breaks into churning, chaotic droplets, splashing every which way, some moving forward, some sideways, some backward, all at once. The clean current dissolves into chaos. Time, at the smallest scale, might be like that churning spray. No single direction, no steady flow, just a boil of moments with no clear order. Scientists find hints of this in their deepest equations. When they try to write the rules for gravity and the tiny world together, something eerie happens. In some of these attempts, time simply disappears from the math. The equations describe a reality with no ticking clock at all, a frozen, timeless picture where before and after have no meaning. Time is not built into the bottom of these theories. It seems to appear only later, higher up, the way heat appears from jiggling atoms or a wave appears from a crowd. That is the staggering possibility. Time might not be a basic ingredient of the universe at all. It might rise up out of something deeper and more timeless underneath, the same way gravity might rise out of information, the same way heat rises out of motion. The flow you feel so surely might be a large-scale illusion, painted over a bottom layer where time does not tick at all. This is still a frontier, still debated, still unproven, but the clue is there, hiding in the math, whispering that the steady river of time might have a strange and timeless source. And if time can lose its meaning at the smallest scale, then something we depend on for our very sanity is in danger too. Because without a steady flow of time, the simple idea that one thing causes another begins to fall apart. Cause and effect, it is the rule your whole life runs on. You knock a glass, and it falls. You flip a switch, and the light comes on. First the cause, then the effect. Always in that order. The past shapes the future. This feels so obvious it barely needs saying. It is the backbone of how you think about everything. But if time dissolves at the smallest scale, as we just saw it might, then this backbone could crack. Without a steady flow of time, without a clear before and after, the simple idea that one thing causes another starts to lose all meaning. Think about what cause and effect really needs. It needs order. The cause has to come first, and the effect has to come second. Knock the glass, then it falls. That order is everything. If you could not tell which came first, the whole idea would collapse. A falling glass that knocks itself makes no sense. Now, bring back the boiling foam of the smallest scale, where time itself churns with no clear direction. Down there, if there is no steady tick, no reliable before and after, then which event comes first might become blurry, fuzzy, undefined. Two tiny events might have no clear order at all, each one somehow both before and after the other, tangled together with no way to say which caused which. Scientists have a careful name for the normal order of things, the reliable rule that causes come before effects. And in some of their attempts to join gravity with the tiny world, that reliable order goes soft. It blurs at the smallest scale. The clean line between cause and effect smears into a haze, just like space smears into foam and time smears into churning droplets. Let me offer a picture. Strange as it is, imagine watching a row of dominoes fall. First one tips the next, then that one tips the next, in a clear, marching order. You always know which domino caused which to fall. Now imagine shrinking down to the smallest scale, where the dominoes flicker in and out of the foam, and the order gets scrambled, so you can no longer tell whether this domino knocked that one, or that one knocked this one. The neat chain of causes dissolves into a jumble where the arrow of because points everywhere and nowhere at once. Feel how deeply this threatens our understanding. Almost everything we know leans on cause and effect. Science itself is the hunt for what causes what. If the very idea goes fuzzy at the bottom of reality, then the foundation under all our knowledge gets shaky. The universe might not have a clean, orderly bottom layer where one thing simply leads to the next. It might have a churning, orderless bottom where the rules we live by only appear once you zoom out far enough. Now, this does not mean cause and effect break down in your kitchen. Up here, in the big world, time flows smoothly and causes come before effects, reliably, every time. The chaos, if it is real, hides far below, at scales you will never touch. The orderly world you live in seems to rise up out of that hidden churning. The same way a smooth flag rises out of countless threads, the same way a calm sea surface hides the storm of atoms beneath. But the mere possibility is staggering. At the deepest level, the universe might not follow the simple story of first this, then that. The order we trust might be something the cosmos builds on top, not something written into its core. To test any of these dizzying ideas, scientists face a monstrous problem. To probe the smallest scale directly, where all of this hides, they would need an amount of power that borders on the unthinkable. By now, you might be wondering something simple. If scientists want to know what happens at the smallest scale, why not just build a machine and go look? We have powerful tools. We have giant machines that smash particles together and reveal the tiny world. Why not just aim one at the smallest scale and see? The answer is crushing. To look directly at the smallest scale, we would need more energy than we could ever hope to gather. Here is why. Remember the rule from earlier, the one that ties tiny spaces to giant energies. The smaller the region you want to see, the more energy you need to probe it. To peer into an atom takes a certain punch of energy. To peer inside the tiny pieces of an atom takes far more. And to peer all the way down to the smallest scale, the Planck length, where gravity and the tiny world collide, takes an amount of energy so vast it defies belief. Scientists actually build machines to do this kind of looking. The biggest one is a giant ring buried underground, miles across, where particles are whipped up to nearly the speed of light and smashed together. It is one of the greatest machines humanity has ever built. It has revealed real secrets of the tiny world, and it is nowhere near powerful enough for the smallest scale. To reach the Planck length, you would need a machine unimaginably more powerful than that giant ring, not twice as powerful, not 100 times. Some scientists estimate you would need a particle smasher so enormous it might have to be the size of an entire galaxy, a ring of machinery stretching across the stars, powered by more energy than a galaxy holds. Only then could you punch hard enough to see the smallest scale directly. Let that sink into your bones. To look with our own instruments at the place where gravity breaks, you might need to turn a galaxy into a microscope. It is so far beyond anything we could ever build that it stops feeling like engineering and starts feeling like a wall around the truth itself. Picture wanting to read the tiniest print imaginable, print so small that to light it up clearly, you would have to focus the power of 100 billion stars onto a single dot. That is the scale of the problem. The smallest scale hides behind an energy wall so high that no civilization, not ours, maybe not any, could ever climb it with brute force. This is one of the deepest frustrations in all of science. The answer to our biggest question about gravity is right there, woven into the smallest scale, present in every point of space around you, and we cannot reach it. It is not hidden far away across the cosmos. It is hidden by being too small, guarded by an energy wall taller than anything we could build. So if brute force is hopeless, if we can never simply smash our way down to the smallest scale, does that mean the answer is lost forever? For a long time, many scientists feared exactly that. They worried that quantum gravity might be untestable, a beautiful puzzle we could never actually check against reality. But a new generation of scientists refused to give up. They asked a clever question. What if we do not need to smash our way down at all? What if there is a sneaky, gentle way to catch quantum gravity in the act, using tiny, delicate experiments small enough to sit on a table? And right now, that daring idea is being tried. For decades, a dark cloud hung over this entire field. Scientists feared that quantum gravity might be forever out of reach. The energy wall was too high, the graviton was too shy, the smaller scale was too small. Many worried that the deepest secret of gravity might be untestable, a puzzle we could dream about but never actually check. Then a bold new idea arrived, and it flipped the whole strategy. What if we stopped trying to force our way down to the smallest scale? What if instead, we let the tiny world's strangeness do the work for us, in an experiment small enough to fit on a tabletop? Here is the clever thinking behind it. The tiny world has a bizarre power. A particle can be in two places at once, spread into a blurry mix of here and there, until something forces it to choose. Scientists have learned to control this strange spreading with great skill, holding tiny objects in a haze of two places at the same time. Now comes the daring twist. Gravity, remember, is caused by mass. Anything with mass pulls on everything else, ever so faintly. So what if you took a tiny object, put it into that ghostly state of being in two places at once, and then asked a simple question? Does its gravity also become two places at once? If gravity is part of the tiny world, if it plays by those strange rules, then the answer should be yes. The object's gravity should also blur into a mix of two places, and this could leave a faint, measurable fingerprint. Scientists have dreamed up experiments where two tiny objects, each in this ghostly double state, are placed near each other. If gravity can pull them together in that ghostly way, it would leave a subtle sign, a tiny link between them that could only appear if gravity itself follows the tiny world's rules. The beauty of this idea is its size. It does not need a galaxy-sized machine. It does not need more energy than the stars. It needs incredibly small, incredibly delicate objects, held in ghostly states, measured with tools of astonishing precision. On a bench in a quiet lab, it sidesteps the energy wall entirely. Instead of shouting at the smallest scale with brute force, it listens for its faintest whisper. Let me give you a picture. Imagine trying to find out if a ghost is real. One way is to build a giant machine to trap it, which is hopeless. A cleverer way is to leave two feathers hanging in a still room and watch to see if they drift toward each other on their own, moved by something invisible. These experiments are like those feathers. They do not try to grab quantum gravity. They set a delicate trap and wait to see if it stirs. This is unbelievably hard. The objects must be kept perfectly still, colder than deep space, shielded from every stray shake and breath and vibration. The signal, if it exists, is heartbreakingly faint. Scientists are still working to make it possible, pushing the limits of what delicate measurement can do. They have not caught it yet, but for the first time, the goal feels reachable. Quantum gravity might be tested not in a galaxy-sized smasher, but on a table, in our lifetimes. If it works, it would answer a 100-year-old question. Is gravity truly part of the tiny world, or something else entirely? And tabletop traps are only one of the new tools, because out in the cosmos, gravity sends us messages of its own, rippling across the universe, and those ripples might carry secrets too. While some scientists hunt quantum gravity on a tabletop, others listen to the whole universe, because gravity does not just pull silently, it sends waves, ripples that travel across the cosmos, and those ripples might carry hidden clues about gravity's deepest nature. Here is one of the most beautiful discoveries of our time. When something violent happens to gravity, when two black holes crash together, for instance, they shake the fabric of space-time itself. That shaking spreads outward in all directions, like ripples spreading across a pond after you throw in a stone. These are gravitational waves, real ripples in space and time, rolling across the universe at the speed of light, and we can catch them. Scientists built giant, incredibly sensitive detectors that can feel these ripples as they pass through the Earth. When a gravitational wave rolls by, it very gently stretches and squeezes space itself. The stretch is mind-bogglingly tiny, smaller than the width of an atom across a detector miles long. Yet our instruments are so precise they can feel it. We have already caught many of these waves, from black holes smashing together far across the cosmos. Think about how astonishing that is. Two black holes collide billions of miles away, and the shudder of that crash travels for a long, long time across the universe, until it finally reaches Earth and gently rings our detectors like a faraway bell. We are listening to gravity itself, ringing across the void. Now, here is why this matters for our journey. These waves are made of gravity. They are gravity in motion, pure and direct, so they might carry fingerprints of gravity's true nature, clues we cannot get any other way. For example, if space really is pixelated at the smallest scale, woven from tiny loops or grains, then a gravitational wave traveling across billions of miles might pick up a faint stutter from crossing all that grain. If gravity leaks into hidden dimensions, the waves might arrive slightly changed, weakened or reshaped by their journey through the extra space. If the graviton, that shy messenger particle, has certain strange properties, it might leave a subtle mark on how the waves ripple and spread. Each of these deep ideas might leave a tiny fingerprint on the waves, if only we can learn to read them. Let me offer a picture. Imagine you could only study the ocean by feeling the waves that reach your feet on the shore. By reading those waves carefully, their timing, their height, their shape, you could learn about storms far out at sea that you will never visit. Gravitational waves are like that. They wash up on Earth after traveling across the cosmos, and hidden in their shape might be secrets about the deepest nature of gravity, written during their long journey. We are only at the beginning of this. Our detectors keep getting more sensitive, and scientists are planning even greater ones, including detectors floating in space, far larger than anything on Earth. With each new machine, we can listen more closely, catch fainter ripples, and search harder for those tiny fingerprints of quantum gravity hidden in the waves. So we are not helpless after all. We have tabletop traps listening for gravity's faintest whisper, and cosmic detectors listening for its distant thunder. Two brand new ways to chase an answer that once seemed impossible to reach. But just as scientists close in, a few daring thinkers have raised a possibility that would upend the entire hunt. What if this whole search rests on a mistake? What if gravity is not part of the tiny world at all? This entire journey, we have assumed one thing. We have assumed that gravity, deep down, must be part of the tiny world, that it must have a graviton, that it must follow the strange rules of blur and chance, that it must join the other forces in one grand rulebook. Almost every scientist has chased that dream for 100 years, but a few daring thinkers have started to whisper a heresy. What if that assumption is wrong? What if gravity is not part of the tiny world at all? This is a radical idea, and it is gaining a small but serious following. These scientists point out that no one has ever actually proven gravity plays by the tiny world's rules. We have never caught a graviton. We have never seen gravity blur into two places at once. We simply assumed it must, because the other three forces do. But assuming is not proving. What if gravity is the lone exception, the one force that stands apart from all the rest? In this picture, gravity would stay smooth and steady all the way down, even while everything else flickers and boils. The tiny world would churn with chance and foam, and gravity would sit calmly on top of it, a smooth force in a jumpy world, refusing to join the chaos. It would mean the two rulebooks were never meant to merge into one. They would stay separate forever, two different kinds of thing, living side by side. If this is true, it would explain some of our deepest struggles in a single stroke. Of course, scientists could never fit gravity into the tiny world's math. Of course, the numbers always exploded into infinity. They were trying to force gravity to be something it is not. They were trying to make a smooth thing jumpy, and it refused. The century of failure would not be a sign that we were close. it would be a sign that we were chasing the wrong dream all along. Let me give you a picture. Imagine everyone assumes that every animal in the forest must be a mammal, warm-blooded and furry. For 100 years, scientists try to figure out how the fish breathes air with lungs, and the math never works. Then a few bold thinkers say, what if the fish is simply not a mammal? What if it belongs to a completely different kind of creature, one that breathes water, one that was never meant to fit the mammal rules at all? Suddenly, the endless failure makes sense. The fish was different all along. These scientists are asking whether gravity is that fish, something fundamentally different from the other forces, wrongly forced into their family for a century. This idea is far from settled. Most scientists still believe gravity must be part of the tiny world, and the search for the graviton goes on. But the mere fact that serious thinkers are questioning the oldest assumption shows how deep the mystery runs. We are so lost that even our starting point is now in doubt. And this leads to the strangest possibility of all. Because whether gravity is quantum or not, a growing number of scientists have begun to suspect something that would change the meaning of reality itself. They think space and time might not be the foundation of the universe at all. They might be something the universe builds later, on top of something deeper. We are reaching the deepest, strangest idea of our entire journey. Through everything we have seen, the boiling foam, the pixelated space, the dissolving time, the hologram, one shocking possibility keeps rising to the surface. Space and time might not be the foundation of reality at all. They might be something the universe builds on top of something deeper. For all of history, space and time were the ultimate stage, the unquestioned backdrop. Everything happened inside space, and everything unfolded through time. Space and time were the container, the bottom layer, the thing you could not go beneath. They just were. But everything we have explored points somewhere stranger. Space boils into foam and loses its meaning at the smallest scale. Time dissolves right along with it. Cause and effect go fuzzy. The whole universe might be a hologram projected from a distant flat surface. Gravity might rise up out of pure information, like heat rising from motion. Again and again, space and time have looked less like the solid floor of reality and more like something built, something that appears, something that rises up out of a deeper layer underneath. So, a growing number of scientists have started to believe the unthinkable. Space and time are not fundamental. They are not the bottom. They are more like temperature, or like a wave in a crowd, real and powerful, and yet made of something deeper that has no space and no time in it at all. Let me bring back the idea of heat one more time, because it is the clearest guide. Heat feels basic, but it is really just atoms jiggling. There is no heat at the bottom, only motion, and heat rises up out of it. Now apply that same thinking to space and time. Maybe there is no space and no time at the bottom of reality. Maybe there is only some deeper stuff, some churning web of pure information or raw connection, with no distance and no duration in it at all. And space and time rise up out of that deeper stuff, the way heat rises out of jiggling atoms, the way a smooth wave rises out of a crowd of separate people. Sit with how staggering this is. It would mean the space around you, the distance between you and your screen, the very room you sit in, is not a basic fact of the universe. It is a pattern, an appearance, something the deeper reality weaves together. And the flow of time carrying you through your day would be woven the same way, rising out of a timeless bottom layer where before and after do not exist. This is where our two great ideas, string theory and loop quantum gravity, and the hologram, and the information idea, all seem to be pointing from their different directions. They keep suggesting that if you dig deep enough beneath space and time, you do not find smaller pieces of space and time. You find something else entirely, something that gives birth to space and time without being made of them. No one has fully cracked what that deeper stuff is. This is the raw frontier, the edge of human knowledge, where the greatest minds alive are still searching in the dark. But the clue is everywhere now. in black holes, in the Big Bang, in the boiling foam, all whispering the same impossible message. Reality might be built out of something that is not space, and not time, and not anything we have words for yet, which forces the ultimate question: if space and time are not the foundation of the universe, then what is? What is reality truly made of, underneath everything we can see and touch and imagine? We have arrived at the biggest question of all. If space and time are not the foundation, if they rise up out of something deeper, then what is that something? What is the universe truly made of, at the very bottom, beneath everything? This is the question that sits at the far edge of human knowledge. And the honest answer is that no one knows for sure. But the clues we have gathered on this journey point toward a few breathtaking possibilities. One answer we have met is information. Maybe the deepest layer of reality is pure information, raw bits of yes and no, this and that, with no space and no time attached. In this picture, the universe is something like a vast computation, and space, time, matter, and gravity all rise up out of how those bits are arranged and connected. Reality would be made of pure difference, pure relationship, and everything solid would be a pattern in that sea of information. Another answer we have met is connection itself. In some of these deepest ideas, the bottom layer of reality is a web of pure links, tiny threads of relationship binding things together, with no distance between them at first. And space emerges from how tightly things are linked. Two things strongly connected end up close. Two things weakly connected end up far apart. Distance itself, the space between things, would be woven out of connection. Reality would be a web, and space would be the shape of the weaving. And gravity, in these pictures, becomes the most beautiful thing of all. Gravity might be what that deeper web looks like when it flexes and shifts. Not a force added on top of the world, but the very shape of the deepest connections, the way the web of reality bends and folds. The pull that holds you to your chair would be the deep structure of the universe, showing its shape through the thing we call gravity. Let me offer one last picture. Think of a great tapestry, woven from countless threads. Step close, and all you see are the individual threads, and how they link, over and under, tight and loose. Step back, and those links blur together into a smooth image, a picture with depth and scenes and space. The image is real, but it is made entirely of threads and their connections. The universe might be that tapestry. Space and time and gravity are the image we see, and underneath, there are only threads, only connections, weaving everything into being. We do not yet know if any of this is right. This is the raw, unfinished frontier, where brilliant people are still searching, still arguing, still reaching into the dark for the true bottom of reality. The final answer might be information or connection, or something no human has even imagined yet, something that will only make sense once we finally understand gravity at the smallest scale. But the direction is thrilling. For the first time, we can glimpse a reality where space and time are not the end of the story but the surface of it, where beneath the world we see, there is a deeper, stranger, more beautiful layer, humming with pure connection, giving birth to everything. And if we ever truly crack this, if we ever reach the bottom and understand what reality is made of, the reward would be almost beyond imagining, because understanding gravity at the smallest scale would not just answer a question, it would hand us a new kind of power over the universe itself. We have traveled a long way, from a simple magnet lifting a paperclip, all the way down to a place where space boils, time dissolves, and reality itself may be woven from pure connection. Now, at the end, let us ask what it would truly mean if we cracked this. If we finally understood gravity at the smallest scale, the answer is staggering. It would rewrite all of physics, and it might hand us powers we can barely imagine. Start with knowledge. Understanding quantum gravity would finally join the two rulebooks that have warred for 100 years. It would give us one single theory for everything, from the tiniest particle to the largest galaxy. It would let us see, at last, what happens at the center of a black hole, where our maps go blank. It would let us peer past the wall of fog at the birth of the universe, and finally answer where everything came from. Some of the oldest questions humans have ever asked would open up before us. But knowledge is only the beginning. Every time humans have understood a force of nature deeply, we have learned to use it, and the world was never the same again. When we understood the force that holds atoms together, we unlocked staggering amounts of energy. When we understood the force behind electricity and light, we built a world of glowing screens and instant messages across the whole planet. Each time we truly understood a force, we gained powers that would have looked like pure magic to the people who came before. Gravity is the one great force we have never learned to control. Imagine what mastering it might bring. Think about what controlling gravity could mean. Today, to leave the Earth, we must burn enormous towers of fuel just to lift a tiny capsule off the ground, fighting gravity with brute force. If we understood gravity deeply enough to shape it, travel through space might become as gentle as sailing. The crushing cost of fighting gravity could fall away. Go further. If gravity really rises out of the deep structure of space and time, then understanding it might mean learning to bend space and time themselves. The very fabric of reality could become something we work with, rather than something we are trapped inside. The dreams that today live only in wild stories, folding distance, reshaping the fabric of the cosmos, might inch toward the edge of possible. We cannot promise any of it, but every one of those dreams begins with the same first step, understanding gravity at the smallest scale. And there is something deeper than any power. There is meaning. To understand what reality is truly made of, to reach the bottom layer beneath space and time and finally see the threads that weave the universe, would be one of the greatest achievements in the history of our species. It would change how every human being understands their place in the cosmos. We would know, at last, what we are truly made of. Right now, we stand at the edge of that mystery. Scientists are listening for gravity's faintest whisper on tabletops and its distant thunder in the ripples of colliding black holes. They are chasing an answer that once seemed impossible to reach. And somewhere out there, hidden in the smallest scale, woven into every point of space around you, the deepest secret of reality is waiting. One day, we may finally understand it, and when we do, the universe will never look the same again. So, the next time gravity holds you to your chair, remember, you are being touched by the greatest unsolved mystery in all of science, and the answer is closer than it has ever been.